Okay, this is chapter 4.5, dilations. Essential question, what does it mean to dilate a figure? And what you will learn is how to identify and perform dilations and how to solve real-life problems involving scale factors and dilations. Okay, so identifying and performing dilations, the core concept for dilations is a dilation is a transformation in which a figure is enlarged or reduced with respect to a fixed point C called the center of dilation. So let me stop right there. Okay, I'm going to go to my highlighter. So C is right here. That is the center of dilation, point C. And by the way, if something enlarges or reduces in size, then it's no longer a rigid motion. So a dilation is not a rigid motion. Okay, so let's continue here. Fixed point C called the center of dilation and a scale factor K, which is the ratio of the lengths of the corresponding sides of the image and the pre-image. So in other words, if I looked at the ratios of PQ to P prime Q prime, then if this was length 2 and this was length 4, then the dilation scale factor would be 2. It'd be doubled. If we go smaller, it'd be fractions, and that's going to say this down below. So a dilation with center of C, scale factor K, maps every point P in a figure to a point P prime, so that the following are true. If P is the center point C, then P equals P prime. In other words, if this point P was at the center C and you dilate it, it will not change. Okay, if it's at the point of dilation, that value doesn't change. If P is not the center point C, then the image point P prime lies on a ray CP, which is right here. So let me highlight that. Here is ray CP right here. Let me make that thinner, of course. Didn't mean to do that. Let's do this. So there is ray CP. So if P is not the center of point C, then the image point P prime lies on CP. So P prime is right here on the ray CP. The scale factor K is a positive number such that K equals P prime C P prime divided by CP. So this side divided by this shorter side. Angle measures are preserved. So what that means is when you do a dilation or a translation or a rotation, then let me get my pad here. If you take this angle, oops, not that one. If you take this angle right here, angle P in this blue triangle, and you dilate the triangle larger, these two angles are congruent. Angle R would be congruent to angle R, and angle Q, I'll put 3 marks, would be congruent to angle Q. Okay, so angle measures are preserved. A dilation does not change any line that passes through the center of dilation. A dilation maps a line that does not pass through the center of dilation to a parallel line. In the figure above, line PR, so let me erase all this stuff. Okay, line PR. Now let's go back to my highlighter and let's use blue and make it thinner. Line PR is right there. In the figure above, PR, line PR is parallel to P prime R prime. These two lines here are parallel. PQ is right here. That'd be parallel to P prime Q prime. And RQ or QR, this side, would be parallel to R prime Q prime. When the scale factor K is greater than 1, the dilation is an enlargement. So if the scale factor is, say, 2, you double it. If this was length 1 and this is length 2, that's a scale factor of 2. If this was length 3 and this is length 6, that would be a scale factor of 2. It got enlarged. The blue triangle became the bigger red triangle. If the dilation is, if K is between 0 and 1, then it's a reduction. So if I change the scale factor to, say, 1/2, then that is what I'm saying. I'm going from this line down to this one. That would be a reduction. You're getting closer to the point of the center point C of dilation. So enlargement greater than 1, dilation between 0 and 1. And that's dilations in a nutshell. Okay, example 1, identifying dilations. Here it says to find the scale factor of the dilation, then tell whether the dilation is a reduction or an enlargement. Okay, so let's take a look. Here's what we're going to use from the core concept on the previous page. If P is not the center point, so this is our P right here, it's not the center C. Same with here, P is here, it's not the center C. Then the image point P prime lies on the ray CP. So P prime is on this CP, this P prime is on this ray CP. The scale factor K is a positive number such that K equals CP prime over CP. So I'm going to write the formula. K equals CP prime over CP. Substitute the givens. CP prime is 12 divided by CP, which is 8. Reduce, simplify. 4 will go into 12 3 times, 4 will go into 8 twice. So the scale factor of this larger safety pin to the smaller safety pin is 3 to 2, or 3 halves. The scale factor is 3 halves, okay? And if I do it again over here, I write the formula, K equals CP prime divided by CP. Substitute the givens, K equals CP prime, careful, it's a shorter one, 18 over CP, 30. So in this case, the original was this big paperclip, and the image is a smaller one. Since it got smaller, it's a dilation, and K is between 0 and 1. So 18 divided by 3 is 6, and 30 divided by 3 is 10. So that is 6/10 or 3/5. Okay, so the scale is 3 to 5, or 3 to 5. You're going from big to smaller, 3/5. All right, so this is 3/5, and it's less than 1, greater than 0. So that is a reduction. And this one is 3 halves. Well, 3 halves is greater than 1. So that is a enlargement. That is an enlargement. Okay, so tell whether the dilation is a reduction or enlargement. This one's an enlargement. This one's a reduction. Now you should be able to do problems 3, 4, and 6 in the exercise. Okay, next core concept is the coordinate rule for dilations. So if P, the point P, is x comma y, all right, so let's look at the graph while we're doing this, or the diagram. So there's P. Right, whoops. Pen's malfunctioning here. P, there's P, is the point x comma y, is the pre-image of a point, then its image after a dilation centered at the origin with scale factor K is the point P prime, which is the scale factor K times X, which gets us up to here, and K times Y, which gets us up to here. So that'd be an enlargement. If P prime is closer to the origin, or the point of dilation, then the K would be a fraction between 0 and 1, and that would make P prime closer to the point of dilation. All right. Okay, example 2, dilating a figure in the coordinate plane. It says to graph triangle ABC with these vertices. So let's do that first. So A, 2, 1, over 2, up 1, that is right here. B is 4, 1, which is here, and C is 4, negative 1. So let me get my straight edge here, if you will, just draw straight line segments, and I'll make them red. So my triangle is right here. So there's my triangle in red. All right, it's off just a hair here. Let me move this in. That's a little better. All right, so there is A, B, C. So A is at 2, 1. B is at 4, 1. And C is at 4, -1. Okay, and then it says, and its image after a dilation with a scale factor of 2. So if we're going to dilate by 2, it's going to be larger. And we're dilating from our 0. So if A is, so what that means is we're going to take every x comma y, and our scale factor, our k, is 2. And if I go back a page, that means that we're going to go from xy to some k scale factor times x, and that scale factor times y. So the scale factor is 2. That's our k. So the formula is kx comma ky. All right, and then we're going to substitute in our givens. So we have the point 2 comma 1 goes 2, and our scale factor is 2 times 2 comma 2 times 1, which will give us 4 comma 2. So I'm going to go over 4 and up 2, and that is going to be A prime. Okay. I'm going to continue now with 4, 1. So it's 4 comma 1 is going to become 2 times 4 comma 1. I'm sorry, yeah, 2 times 1, which will give us 8 comma 2. And unfortunately, I'm just off over here, but I'll estimate. So here's 8, here's 7, here's 8, up 2. That is B prime. And then finally C. So this was A, this was B, and this was C, and this is A prime, B prime, and C is the point 4, -1. And that is going to become our scale factor times 4, comma, our scale factor times -1. And that is going to give us 2 times 4, which is 8, and 2 times -1, which is -2. And that's where C prime will end up. So I go over to 8 again and down 2, and that's here, and that is C prime. And then if I make that a triangle now, then it's going to go from here to here. What happened to my blue? Let's try that again. This, go here, go here, go here, blue, and we're going to draw this to here, down, and over. All right, so there it is. Let me just move this A, B a little bit. And so there's A prime, B prime, C prime. So as you can see, this is a length of 2. This is a length of 1, 2, 3, 4. This is a length of 2. This is a length of 1, 2, 3, 4. And this diagonal is 2 diagonal squares. This would be 1, 2, 3, 4 diagonals. Okay, so that is how you dilate a figure in the coordinate plane. Now you should be able to do example 3. I'll go over first because 2 and 3 are very similar. All right, example 3, dilating a figure in the coordinate plane again. Here's another example. And we're going to graph the quadrilateral KLMN with vertices of these and its image after dilation of a scale factor of 3, or 1/3, I mean. Okay, so there's a scale factor, these 3. So K is, I'll do this in green, K is -3, 6. So it's all the way up here at the top. L is 0, 6. So this is K. This is L. M is 3, 3. And N is -3, -3. So this is M, and this is N. All right, so now I'm going to connect them. And green. So K, L, L, M, M, N, N, K. All right, so there is our quadrilateral KLMN. And now we're going to dilate it a scale factor of 1/3. So what I'm going to write here is K equals 1/3. That means it's between 0 and 1, and it is a reduction. So if I take the point K, actually, let's write the rule first. It's going to be X comma Y becomes 1/3 X comma 1/3 Y. So my first XY, which is K. Struggling here. K is the point -3, 6. And that becomes 1/3 times -3, comma, 1/3 times 6. And that's going to become 1/3 times 3 is 1, and it's -1, comma, and 1/3 of 6 is 2. So I'm going to plot the point -1, 2 right there. That is K prime. Notice it's closer to the origin than K was because it's a dilation reduction. So then we go to L. The point L is 0, comma, 6. Our rule says to multiply x by 1/3 and multiply y by 1/3. That is going to give us 1/3 times 0 is still 0, and 1/3 of 6 is 2. So my point is 0, 2, and that's my L prime. So it went from 3 down to a length of 1, and that is 1/3 of 3. All right, so then we go to M. All right, M, 3, 3. 3, comma, 3, arrow. That's 1/3 times 3, comma, 1/3 times 3. And that is going to yield 1, comma, 1, which is right here. And that is M prime. And then finally, N is -3, -3. And that would be 1/3 times -3, comma, 1/3 times -3. And that is going to give us -1, comma, -1. Left one, down one, and that is N prime. Get my ruler if I were doing this on paper for a nice straight edge. I'm going to use my straight segment tool and draw this like so. And there is quadrilateral K prime, L prime, M prime, N prime, which is 1/3 the size of the pre-image KLMN. All right, so now after example 2 and 3, you should be able to do numbers 15, 16, and 18. Okay, just a quick note before we get on to our next example. So here is a diagram. The pre-image is the blue trapezoid. Scale factor of K, where K is greater than 1, is the gray one, further away from the center of dilation, which is our origin. And now we're going to talk about in the coordinate plane, you can have scale factors that are negative numbers. When this occurs, the figure rotates 180 degrees. So when K is positive, a dilation with a scale factor of -K is the same as a composition of the dilation with a scale factor of K followed by a rotation of 180 degrees, about the center of dilation. Using the coordinate rules for the dilation and a rotation of 180, you can think of the notation as x comma y becomes x or k, our scale factor, times x times k, our scale factor times y, which then results in a -kx comma -ky. So you first enlarge it by k, and then the negative would be 180-degree rotation besides the dilation. So let's take a look at that. Okay, example 4 is using a negative scale factor. So here's the example for that. So it says graph the triangle FGH with these vertices. So let's do that. F is -4, -2, left 4, down 2. There is F. G is -2, +4, which is here. And that's G. And H is -2, -2. So here is H. So then I get my ruler, if you will. I'm just going to use this tool. You would use a ruler on paper. All right, so there is our triangle FGH with those coordinates. So what we're going to do now is we are going to scale it by a factor of -1/2. I brought the rule over. It's xy becomes k times x times comma k times y, which is then going to be -k times x times comma -k times y. You don't need to do this middle piece. You just need this part. All right, do it in one step. So xy, I'll start with f. F is -4, comma, -2. And I'm going to take this, which is our k. Okay, that is k, -1/2. So it's going to be -1/2 times my x, comma, -1/2 times, whoops, times my y. Guess I don't need that dot. So it's -1/2 times -2 and close the parentheses. So this is going to give us negative times a negative is positive, and 1/2 of 4 is 2, comma, negative times a negative is positive, and 1/2 of 2 is 1. So that is f prime. So I'm going to go over 2, up 1, and that is f prime. Continuing with that, the next one is g. And you should always show all your work. G is -2, 4, -2, comma, 4. And we're going to go to -1/2 times -2, comma, -1/2 times 4. And that is going to become negative times a negative is positive, 1/2 of 2 is 1, and negative times a positive is negative, and 4 times 1/2 is 2. All right, that's a 4 right there. Let me fix that. It's hard to read. This is a 4 in parentheses. Okay, so that's going to be -1/2 times 4, -2, and that is my g prime. So over 1, down 2. That is g prime. And then finally, h. H is the point, -2, -2. And then we're going to go to -1/2 times x, which is -2, comma, -1/2 times y, which is -2. And obviously they're the same, so 1/2 of 2 is 1, negative times a negative is positive. I'm going to end up with the point 1, 1, and that is my h prime. Over 1, up 1 is right here, and that is h prime. And get my pen, purple, and draw your segments. So as you can see, it's 180-degree rotation, and it's half the size, because FH is 2, F prime, H prime is 1. Okay, so there is a dilation by a scale factor of a negative. It's a dilation of 1/2 followed by a 180-degree rotation. So now you should be able to do 19, 20, and 22. Hey, okay, I'm sorry, I was just doing a selfie there. They made me want to do a selfie because they were doing a selfie there. But anyway, solving real life problems, finding a scale factor. Example 5, you're making your own photo stickers. Your photo is 4 inches by 4 inches. So this photo right here is the original 4 by 4. Okay, its image on the sticker is going to be 1.1 inches by 1.1 inches. So it's this tiny little sticker that's smaller than the original. So we're going from a large image to a smaller, or large pre-image to a smaller image. Therefore, if we think of this rule here, k has to be between 0 and 1, which means the numerator is less than the denominator. Think about that, okay? So you're making your own photo. What is the scale factor of this dilation? Remember, scale factor is k equals cp prime over cp, where cp prime is the length of the side of the image. Okay, so let me highlight that. So this is my numerator. This is my denominator. Okay, the original, and the prime's the image. So show your work. You would say k equals, okay, it says what is the scale factor? Scale factor is k. K equals the length of the side of the image, 1.1, divided by the length of the side of the pre-image, 4. Okay. And there it is. That's pretty much it. Can you reduce that? Well, if you don't want a decimal and a fraction, because that's kind of a fraction within a fraction, we don't want that. Multiply 1.1 by 10 to move the decimal over 1, and that'd be 11. Multiply 4 by 10, and that is 40. So the scale factor is this, and this is 11 over 40. Okay, what is the scale factor of this dilation? 11 over 40. It's less than 1, right? 11 divided by 40 is less than 1, but greater than 0, because 40 over 40 is 1, and 11 over 40 is less than that. So there you have it. And it's a reduction. The sticker's smaller than the picture. All right, so there's that one. Now you should be able to do problems numbers 29 and 30. Okay, example 6. Let me get my highlighter, and I'll use, I don't know, purple this time, or whatever that color is. Example 6, finding the length of an image. You are using a magnifying glass that shows the image of an object that is 6 times the object's actual size. 6 times. That's a little bit large. Let's go to here. 6 times the object's actual size. Determine the length of the image of the spider seen through the magnifying glass. Okay, so remember, it is this rule right here. All right, K equals CP prime over CP, where the new image, the copy of the pre-image, is on the top and the pre-image is at the bottom. So here we go. So now we know what K is. 6 times the object's actual size, that means K equals 6. Okay, so we want the image length. So we want the image over the pre-image. The image over the pre-image has to equal our K. So this is the pre-image here. We know that. So that's, we substitute our givens, 1.5. We don't know what the image is going to be, but we do know that our scale factor is 6. So what value, after looking at this spider in the magnifying glass, divided by 1.5 will give us 6? Well, in order to solve this, we just simply multiply both sides by 1.5. And the 1.5s cancel, and I get my x to equal 6 times 5 is 30. Carry the 3. 6 times 1 is 6, plus 3 is 9.0. And use your unit of measurement in your answer, centimeters. Okay, so there it is. Taking a 1.5 centimeter spider, looking at it in a magnifying glass that magnifies it 6 times. That object would then look like it is 9 centimeters long. Okay, so there you have it. Okay, so that brings us to the end of chapter 4.5. So here is the list of exercises that you should do to get used to and learning the process of dilations. Have a great day.